So, last time we saw that the ring of integers in a number field is a Dedekind domain, and in particular we proved that if P is a non-zero prime ideal inside the ring of integers, then then OK mod P is a finite field. Okay. And this notion was used to define norm of an ideal, and we want to prove that norm is multiplicative, completely multiplicative. So, norm of product of two ideals is product of norms of those ideals, and to that end we so this is what we will prove today, and this is for a general Dedekind domain. So, let R be a Dedekind domain and P be a non-zero prime ideal in R. Okay. Then R mod P is isomorphic to P to the n minus 1 mod P to the n for n bigger than or equal to 1. Okay. And our convention of course is that P to the 0 is R. So, in case of n equal to 1 there is nothing to prove. So, here is a proof again of this. So, this is an isomorphism as R modules. Okay. All right. So, how is this isomorphism obtained? So, we define a map phi from R to P to the n minus 1 modulo P to the n. And how do we define this map? So, you take and fix beta in P to the n minus 1 minus P to the n. So, P to the n minus 1 is strictly bigger than P to the n. So, there exists such a beta, and you put phi of x to be x times beta. Okay. And then we observe that kernel of phi is actually P. So, we get an injective map phi from R mod P to P to the n minus 1 modulo P to the n, and we want to prove that this map is also surjective. So, let alpha be an element in P to the n minus 1. Now, we are going to use Chinese remainder theorem. So, we find x in R such that x is congruent to alpha modulo P to the n, and x is congruent to 0 modulo the ideal generated by beta over P to the n minus 1. So, because beta is contained in P to the n minus 1, but not in P to the n, if you take the prime factorization of the ideal generated by beta, P to the n minus 1 will appear in the prime factorization, but P to the n will not. Okay. So, these two ideals are co-prime. So, you can use Chinese remainder theorem to find such an x. Okay. Once you have found such an x, what you can do is, so let me call this x 0. Okay. Once you have found such an x 0, you can put x to be x 0 by beta. Okay. And then the claim is that this is actually in the ring of integers of the number field k. And why is that? Well, you will just look at the prime factorization of x, right. You look at the prime factorization of x, then in that prime factorization no element appears to negative power, because the only negative powers can come from beta, but x 0 is in beta, right. I mean x 0 is in beta by P to the n minus 1. So, no prime other than P can appear in the denominator of prime factorization of x, and P to the n minus 1 does not appear because x 0 is contained in P to the n minus 1. Okay. So, so this is in this, and phi of x is equal to alpha. Okay. So, phi is surjective. Okay. So, in particular the corollary of this is that if P is a non-zero prime ideal, in OK, then the index of P to the n in OK is same as norm of P to the power n. Okay. And why is that? Well, this process is very important, has even a name in mathematics, is called Devisage, and this is, so let me emphasize this. So, you have OK, it contains P and it contains P squared and so on up to P to the n. Okay. And so, what you have is index of P to the n in OK is same as index of P to the n minus 1 in OK and multiplied by index of P to the n in P to the n minus 1, right, and we can keep going. So, what we get is OK, P and so on. So, let me write one more term here, and that is the wrong term. So, the next term here is P, P squared and so on up to P to the n minus 1, P to the n. But we know that each of this index is same as index of OK to P to the n, which is norm of P to the power n. Okay. So, that is quite nice, and this already proves that norm of P to the n is this. So, norm is multiplicative for powers of primes at least, right. So, that is the, yeah, so that is the corollary here, all right. And now we are going to prove the following things. So, lemma, let A and B be fractional ideals of OK, right. Then norm of product of AB is same as product of norm of A and norm of B. So, you can either take product first and then take norm, or you can take norm first and then take product, it gives you the same number. So, what I will say is that you can assume A and B are integral ideals, and if this is not clear to you, then this is an exercise enough to prove the lemma. Just by the way norm is defined, this is easy to figure out, enough to prove the lemma for integral ideals. Okay. Now, I can write my integral ideal, I can take its prime factorization P1 to the A1 and so on, Ps to the As, right. I know that OK mod A is isomorphic to product over I going from 1 to S, OK modulo Pi to the Ai. So, Pi's are all distinct primes, Pi is not equal to Pj if I is not equal to j. This is a version of Chinese remainder theorem that we proved. Okay. So, hence norm of A is equal to product over Pi's, right. So, product over I, norm of Pi to the Ai, but we just proved on the previous page that this norm is equal to norm of Pi to the power Ai. and the same thing would hold for B as well. So, norm of B will be product over J, norm of Qj to the Bj if B has the prime factorization J going from 1 to R, let us say Qj to the Bj, right, and hence norm of AB is equal to norm of A times norm of B. Right. So, we get this very nice multiplicative property for norms. Just like we have multiplicativity property for norms of elements, we also have multiplicativity property for norms of ideals, absolute norm defined this way. Okay. All right. So, now we have proven that ring of integers in a number field is a Dedekind domain. So, prime factorization holds for these things, right. So, we are going to study this more systematically for extensions of number field. Okay. So, the situation that we put ourselves in is the following. So, let L over K be a finite extension of number fields. Okay. So, it is good to draw a diagram like this, and I will keep drawing such diagrams again and again throughout. Okay. So, K is my number field, and then OK is the ring of integers in that, L is my number field, and OL is my ring of integer in that, and then I have a prime ideal P here. So, this is a non-zero prime ideal. Now, what I can do is I can consider what is called extension of P to OL, right. What is this? This is P times OL, this is the ideal generated by P in OL. P was a prime ideal downstairs in OK. I take the ideal generated by P in OL. This need not be a prime ideal at all, right. It does not have to be a prime ideal, but it is a non-zero ideal. So, POL is a non-zero ideal of OL. Okay, and warning that POL need not be prime. Okay. It is an ideal of OL, it is a non-zero ideal, but just because P is a prime ideal, POL need not be a prime ideal. In any case, as OL is a Dedekind domain, POL has a prime factorization in OL. Okay, so, P times OL is P1 to the E1 and so on up to PR to the ER. So, these are the usual notations where PI's are prime ideals in OL. So, these are distinct prime ideals in OL. So, here is a definition: each prime Pi is said to be above P, okay, and P is said to be below Pi, sorry, capital Pi for each I, right. So, this is because of the diagram. So, let me recall the diagram here again. Inside I have P, here I take POL, but this thing is now product of P1 to the E1, PR to the ER, right. And so, each of this Pi is above small p. Later on I will prove that Pi intersected with OK is exactly small p, and so it will make more sense I think this way, but I can give the definition right away. Okay. EI is called ramification index. So, this is either ramification index of Pi in L over K, but I will usually not say so many words, I will just say EI is ramification index. Okay. All right. So, these are very important invariants, ramification index, this prime above a given prime, prime below given set of primes, etc. These are very important invariants, and this is we will spend most of our time studying how a given prime factorizes in an extension, how to calculate ramification indices, and some other indices that I am going to define now. Okay. So, as I said, I am very fond of this diagram of extensions of fields. So, I keep drawing it again and again, right. So, now inside this I have P, and then I fix one Pi above this, right. So, this is above this, and what I can do is I can look at OK mod P, okay, and then I look at OL mod Pi. So, what I am going to do is right, okay. So, this thing is also denoted as, so notation is P divides each Pi divides P. So, another way of writing something is above or below is like this. So, Pi divides P. So, here Pi divides P. So, I fix any such thing, and here is a lemma that I want to prove. Okay. So, these are both finite fields, right, and what we are going to prove is that OL mod Pi is a finite extension of OK mod P. Okay. We know that these are both finite fields, and I want to show that this is a finite extension. Okay. All right. So, how do I prove this? Well, I take the following map. You take OK. So, OK is a subset of OL. So, there is an injective map like that, and I can further compose it with the quotient map, right. All right. So, and now I know that this is a finite field. So, let me call this map phi. Okay. So, what is kernel of phi? Kernel of phi is precisely OK intersected with Pi, all right. And then I want to show, so my claim is that P is contained in OK intersected with Pi, right. So, remember that POL is P1 into E1 and so on up to PR into ER, which is contained in PI. So, in particular P is contained in PI, right, and of course, P is contained in in OK. So, hence P is contained in OK intersected with PI, right. And so, what we have is P is contained in kernel of phi. Okay. So, phi induces a map, a ring homomorphism from OK mod P to OL mod Pi, but these are both fields, right, and if you have a ring homomorphism from one field to another field, it better be injective. Are finite fields, hence phi from OK mod P to OL mod Pi is injective, and that is what it means for OK mod Pi to be a field extension of OK mod OL mod Pi to be a field extension of OK mod P. So, here is a more notation. We denote by KPI this OL mod Pi, this is a finite field, and then Kp is OK mod P, right. So, these are called residue fields. So, that is the name, and then Fi is degree of these this field extension, and this is called residue degree of Pi. So, again an important invariant. So, ramification index, residue degree, okay, and then R is the number of primes above prime P. So, these are important indices, and now I am going to give you an important relationship between these indices. So, here is a proposition. Let L over K be a finite extension of number fields and I denote its degree by n. Let P in OK be a non-zero prime ideal okay, so it is a maximal ideal, and when you extend P to OL you get P1 to the E1 and so on up to PR to the ER. Okay, so, this is just a piece of notation. Then n, which is degree of L over K, is related to all these indices as follows. So, you take EI and FI, you take product of EI and FI and you take their sum, this is what will give you n. Okay. All right. So, we want to prove this. So, let us first prove this in the case when k is equal to q. Just for simplicity, it does not really matter, it helps you understand what the proof is. So, first assume k is equal to q, right, and so you can just take P O L this is P1 to the E1 and so on up to PR to the ER, right. Okay. So, then what you do is you take norm of both sides. So, take norm of both sides, and because it is on other page, let me rewrite it here. So, we are calculating norm of the same thing in two different ways. So, what is norm of POL? Well, we proved that this is equal to norm from L to Q of P mod of that times norm of okay. So, norm of OL, but norm of OL is just 1, right. This is equal to 1. So, this is P to the degree of L over Q. Okay. On the other side, what is norm of P1 to the E1 up to PR to the ER? Well, we know that norm is surjective. So, what this is product I going from 1 to R norm of Pi to the EI, right. Okay. So, now my claim is that norm of Pi is equal to P to the Fi, right. Okay. And perhaps I should have written this as a corollary when I proved this. So, we proved that there is an injective ring homomorphism from OK mod P to OL mod Pi, right. But in our case, so when k is equal to q, OK mod P is just Z mod Pz, right. This proves of course that this implies that OK intersected with Pi is equal to P. I should have remarked that when we proved the injectivity of this map, but it is clear that it implies this. Furthermore, OL mod capital Pi is extension field extension. So, this is the finite field Fp, field extension of Fp of degree Fi. Therefore, the number of elements in OL mod Pi, this is the number of elements in Fi to the power the number of elements in Fp to the power Fi, right. So, norm of Pi is equal to P to the Fi, right. That is what we wanted to prove, that is what the claim was. And so, we get norm of P1 to the E1 PR to the ER is equal to P to the summation EI Fi, right. Therefore, degree of L over Q is equal to summation I going from 1 to R EI Fi, right. So, that proves the lemma in this particular case, at least when k is equal to q. Okay. So, what we have done today is we looked at how a prime fact in a number field, when you extend it to a bigger number field, how it factorizes, and we defined important invariants attached to it like ramification index, residue degree and number of primes above it, and we proved a relationship between degree of the field extension and all these other invariants, at least in the case when the ground field is when the base field is rational numbers. And next time we are going to finish the proof when the for arbitrary base field, and then we will define what is called the ideal class group. Okay. So, thank you.